with these foundations, we can actually proceed to an important topic. That's 1.6, classification of sets. Now this is an important exercise. Every time you define a notion in mathematics, you immediately ask, what is the classification? How many different objects of this type do I have? How do I get an overview over this structure? It's fine to write down a definition. It's fine to write down, in this case, 9 axioms. But we would like to have an overview. What type of, in this case, sets are there? But this is something that doesn't only happen in set theory. It's a recurrent theme in mathematics. So let me write this down. A recurrent theme in mathematics is the study, well, study is very general, let's be more precise, is the classification of spaces. I'll explain in a second what a space is supposed to mean. It's the classification of spaces by means of structure-preserving maps between those spaces. So we have to clarify what we mean by spaces, and we've got to clarify what we mean by maps. A space is usually meant to be some set together, or let's say equipped with some structure. And in the beginning of the course, I told you that we'll put layers of structures on top of each other. So we'll equip sets with more and more and more structure. And that's the structure I'm talking about here. So it will be topology as the next step, then it will be a differentiable structure, and so on. Okay, but it could also be other structures like a group structure. So you give an operation on a set, and so you add structure like this. And every time this principle applies, a space is usually meant to be some set equipped with some structure. And now you want to classify such a space. Well, the case of sets is, of course, a trivial instance of this because it's a set without additional structure. Okay, fine, but it's nevertheless a set, and a structure-preserving map in the case of set theory simply becomes a map because there's no structure that could be preserved. Well, it's the structure of the set itself, but it's kind of the lowest level structure, and we'll investigate this. And the set has structure. So this is this. So obviously we need a notion of map. Definition. A map phi is a relation. Well, it's a map phi from a set A to B is a relation such that for every A in A, there exists exactly one B in B, such that phi A comma B, full stop. What does it mean, phi of A, B? Well, it means phi of A, B is true. You remember, a relation of two variables can be true or false, and if A and B are sets, then a map from A to B is such a special relation such that it exists for every A exactly one B in B. Now, our standard notation for this somehow hides the fact that phi is a relation, that it eats two variables and produces a truth value. The standard notation for this is to write phi AB and then to write A to the value A in A, we assign the value phi of B in B. And you see, if you say phi is a relation, then this is an abuse of notation because the relation needs to eat two objects and produce a truth value. But once we agreed that for every A in A there exists exactly one B in B, such that phi of AB, then phi of B, phi of A. Then phi of A is precisely this B. Okay, so this is then defined as precisely the B that's unique such that phi of AB is true. And that's the standard notation, right? But structurally speaking, well, I don't know whether it's important, but it's at least structurally correct to keep in mind that a map is actually a relation. If you don't look at a map as a relation, then you get into trouble because you have to say, well, a map is such that to every A there is assigned a unique B. The question is, what do I mean by there is assigned a certain B? What does it mean to assign to one element in A another element in B? This notion of assigning is not defined, and so it comes from a relation. Okay, so that's the basic idea of a map. So there's some further terminology. So if you have a map phi from A to B, then A is called the domain of the map. B is called the target of the map. Then there is an object that we write down as phi of A, or sometimes we write it down as the image of the set A under the map phi, and is nothing but the set defined by restricted comprehension is the set of all phi of A, where A comes from A, and of course we know that this must lie in B by definition, so it's really restricted comprehension. We can define it like this. This is the image. And then we have further definitions, also well known to you, that a map phi from A to B is surjective if its image phi of A coincides with the target. So if every point in the target is hit by the map, it's injective if the equality of two values of the map, if phi of A1 equals phi of A2, already implies that A1 equals A2. And the map is bijective, and that's the key notion. It's bijective if it's injective and surjective. And bijective is the by far most important notion. And in fact, we have the following key definition. Two sets, A and B, are called, I put the qualifier here, set theoretically isomorphic. So they're called isomorphic in set theory. And for this we write A equal with a twiddle on top B and the qualifier set as a subscript. It's called isomorphic if there exists a bijection, let's call it phi, from A to B. Now you see, we just require the existence of some bijection. And by not asking for a particular bijection, how would we? Actually, this becomes a property of the two sets. They are such that there is such a bijection. Important remark is, if there is any bijection, there is any bijection at all, from A to B, then generically, that means only in exceptional cases it's not the case, then generically there are many. That means there is not a unique such bijection. The whole criterion is there exists such a bijection. And the intuition about this is pair up elements of A and B. So if you have two classrooms, one with boys and one with girls, you can ask, are they isomorphic? All you got to do is pair up the boys with the girls in pairs. And if there's nobody left, then obviously you have a bijection, because to every boy you find a girl. But you find exactly one girl, so it's injective and surjective, and every girl gets a boy, or gets assigned to a boy. Then you have the intuition of equal size. But it's actually better than an intuitive notion of equal size, because it also works, and it's designed to work, for infinite sets. For finite sets, equal size is an easy thing. You just count, you say it's the same number. But for infinite sets, that's not so easy. By the way, we could clarify what an infinite set is. And that's already the promised classification. Classification of sets. By way of studying structure-preserving maps, and the structure-preserving maps are the bijections in the case of set theory. Classification of sets. A set A is, let's start with the definition of infinite. Infinite if there exists a subset, a proper subset, if there exists a proper subset. What's a proper subset? It's a subset, but by force it's not equal to the set. There exists a, so the set A contains an element that the set B does not contain. Okay? It's infinite if there exists a proper subset. Well, that's not it yet. If there exists a proper subset that is isomorphic to A. So B, in fact, set theoretically isomorphic to A. Now for finite sets, that's an immediate contradiction. If you have a finite set A and you have a proper subset, say the finite set 1, 2, 3. You have a proper subset, the set 1 and 2. Okay, it's a proper subset. Then 1, 2 is not isomorphic to 1, 2, 3. You don't find a bijection there. So for finite sets, this seems impossible. But it is precisely the signature of an infinite set that there exists a proper subset, such that the subset, however, is still isomorphic to A. So a typical example would be the integer numbers z and the natural numbers n. Right? N is a proper subset of z, because -1 is not in n. That suffices. Okay? But nevertheless, z is isomorphic to n. You can make a bijection. Okay? You can write down a bijection. So that is infinite. Now, if it's infinite, there are two different types of infinite. A set is called countably infinite. So A is called countably infinite if A is in fact isomorphic to the natural numbers, to the non-zero, the non-negative integers. Intuition is if you can label the elements of a set. If you can attach a label to everything, this is number 1, number 2, number 3. If you can label all the elements, the set is called countably infinite. And the set is called uncountably infinite otherwise, called non-countably infinite otherwise. And then a set is called finite, again, otherwise. But now the otherwise, of course, refers to this level of the structure if it's not infinite. Okay. Fine. So that's the classification of sets. And there is not more to be said. Well, maybe that if you have a finite set, A, in this case, A will be set theoretically isomorphic to the set 1, 2, up to an integer number n for some n in the natural numbers, and then write that the size of A is n. There are n elements in A. That's the classification. Any questions so far? Okay. So, some more words on maps. Well, given two maps, so the first thing is that given two maps, we can build a new map. You see, it's always the same. Given two maps from A to B, and sometimes it's convenient to denote the map on top of the arrow, from A to B, and another map from B to C, let's call this other map psi. Given two maps, one can construct a third map. In this case, the map with name psi after phi. So we read this after psi after phi, which is a map from A to C, and it assigns to A the value of psi of phi of A. That's the composition of maps. Composition of maps. And very often the situation is diagrammatically represented by writing a diagram A, B, arrow, phi on top, that's like the first piece of data. From B to C, it's the second piece of data. And then you write here psi after phi. And if you're very precise, you say that this diagram commutes. But very often, people don't write this explicitly, but by writing down this diagram, they say, there it is, it commutes, which means you can go this way or you can go that way, and if you start from here, you arrive at the same result. And if then this arrow is called psi after phi, that obviously defines psi after phi. The element in A is first mapped by phi, and then the result is taken on by psi and mapped to C, and this is this map. And well, this might seem overkill as a notation, but we'll later on meet situations where many maps go from many places to many other places, and then actually these diagrams are much more convenient than writing down the data in the traditional way. Now, quite obviously, but it needs to be checked, but it's a one-liner, obviously composition circ, and this circ obviously is an operation on the space of maps, because of two maps it makes a new map, but only if the target of the first map, well, this map, is the domain of the other map, obviously. So obviously composition circ is associative. So if you have a third map, psi after psi after phi, and you first evaluate this, then it ought to be the same, and it is the same as psi after psi after phi. Okay, composition is associative. Now, you need a composition in order to be able to speak of an inverse map. If you have no composition, you can't speak of the inverse map. Definition. Let phi from A to B be a bijection. So only for bijections we define the following. Then the inverse of phi is the map phi up to the -1, of course just means inverse, from B to A, defined uniquely, so there's no ambiguity, defined uniquely by phi inverse circ phi, so you need the circ in order to speak of the inverse, phi inverse circ phi. Well, let's, for practice, write the diagram. A, B, phi goes like this, phi inverse goes like this. So if you phi inverse after phi, you go back to A, you require that the result is the identity on A, and if you go the other way around, phi after phi inverse, then it's the identity on B, and the identity on a set M is a map from the set to the set where every element of the set gets assigned to itself. That's the identity map. Which obviously we have for every set. Okay, so an inverse only exists for bijections. Now, however, another notion which we're going to meet in topology particularly is the notion of a pre-image, and the pre-image is kind of something like the image of the inverse, but actually the map you look at doesn't need to be a bijection, it can be any map. So let phi from A to B be any map. Then we define the set pre-im, like pre-image, of a set V. Well, and this set V is supposed to be a subset of the target of the map. And the pre-image of V under the map phi is defined as all those A in the domain whose image under phi lies in the specified set V. Okay. Now, if you have a bijection, then the pre-image of an individual element will always be a set with a single element, obviously. If you have a non-bijection, then the pre-image of a one-element set can be a set with several elements. Okay? But so the pre-image is always a set. It's called the pre-image of the set V in the target with respect to WRT, with respect to the map phi, pre-image. All right? It's all basic notions. It's convenient to fix notation once and for all. So that was the classification of sets. And before we leave set theory, there's one more topic, or well, one of two more topics I would like to talk about, and that's equivalence relations. I try to be very quick about this because I assume that in one form or the other you saw this before. I just want to demonstrate how to get this from the basic axioms and that everything is fine, if you will. And well, equivalence relations provide a heavily used way to look at a set, but to give it structure in a certain way. In which way? By identifying certain elements in a set. Okay? Not in any way, but in a way that we will call an equivalence relation. Actually, much of our thinking is in equivalence relations. So if I come into this classroom, I might, or say somebody else comes into this classroom, they might think of you as one entity and of me as another entity. There's the class and there's the teacher of the class. Okay, great. But then the thinking might change, and he might want to look at all of us of the same gender, classify us according to gender, and he'll say, okay, there are this many men, there are this many women. And our thinking flips back and forth between regrouping things that are there, okay, and looking at sets in a coarser way, therefore. Okay, and in order to group a set entirely so that really no one is left out, and that there are no intersection between the groups, one employs very cleverly equivalence relations. So the definition is simple. Definition. Let M be a set and twiddle a relation such that there are three axioms to be satisfied. The first one we call reflexivity, such that reflexivity holds. Reflexivity means that for all M in the set M, it is true that M twiddle M. And you remember our convention that this means twiddle M is true. But if we have a relation, we very often put the relation symbol in between the two arguments because this saves chalk. Second, there must be symmetry in the following sense. If M and N are elements of M, and assume it's already clear that M twiddle N, then that's supposed to be the same as N twiddle M. And the third condition a relation needs to satisfy in order to qualify as an equivalence relation is that there's transitivity. Transitivity means that for all M, N, and P in a set M, if it's clear that M twiddle N is true, and additionally N twiddle P is true, then it must be true that from this it follows M twiddle P. So let M be a set and twiddle a relation such that these three axioms are satisfied, then twiddle is called an equivalence relation on M. Now, some examples are in order. So let's say first example, let's define P twiddle Q. By definition, this is supposed to be that P is of the same opinion as Q is. Let's think of them as human beings. Then it's clear this is reflexive. I mean, so let's say they are mentally sound human beings, okay, you have your own opinion. It's reflexive. It's also symmetric. If I agree with someone, then that person agrees with me. And it's also transitive. So if you wish, this is the basis for democracy. Okay. B, let's say we define a different equivalence relation. Like P is the sibling of Q. Sounds good, but it already fails to be reflexive because you're not your own sibling. Not reflexive. So here it is an equivalence relation. This is not an equivalence relation. P is the sibling of Q. It would be symmetric, though. But symmetric. Let's say P twiddle Q defined as P is taller than Q. This would be perfectly transitive. Yeah. But it's not reflexive. Could make it reflexive if you say taller or equally tall then, okay? But certainly it's not symmetric generically, okay? So it's certainly not symmetric and therefore fails to be an equivalence relation. And then my favorite is P twiddle Q. P is in love with Q. So this is not reflexive on occasion. There are people who don't like themselves very much. It's certainly not normally symmetric. That's the basis of much drama in literature. And it's not transitive. Maybe only in French movies, French art cinema, it's transitive. All right, so only the first one is really an equivalence relation. And you see, it's very easy to check whether something is an equivalence relation. And if it is, there are important constructions one can make. And these constructions have interesting properties. That is why you want to check. And we have the central definition. If twiddle is an equivalence, or B, an equivalence relation on the set M, then for any element of M, we define a set, define the set, and the set gets a funny name. It's M with square brackets around it, but it's a set and has a simple definition. Those are all those elements N of the set M which are equivalent to N. So once we have an equivalent relation, we very often read this as M is equivalent to N. Okay, the set, and this set is called the equivalence class equivalence class of this element M. Now, for these equivalence classes, there are two key properties. And the first property is that if you take an element A from such an equivalence class is a set, it's a subset, it's obviously a subset of the entire set. Right? So if you take any element from this subset, then it already follows that the equivalence class of this element you took from the subset is already the same equivalence class. Or in other words, one says that any element of the equivalence class can act as a representative of the equivalence class. So that's taking it the other way around. If you start with an element, you build this set. Okay? But if you already have this set, you can take an element out of it and you can generate the set in the same way from that element. So this is usually interpreted as A is, or any element of an equivalence class can act as its representative. Okay? That's just a notation in the terminology. And the second key property is that one of two things holds. Either two equivalence classes for two different elements are the same, or if they're not the same, then they have no element in common. That means the intersection is empty. And there's no other possibility. Two key properties. A proof is very simple. Simple. And you should do it. Now, the intuition about this is the following. Assume you got the set M and you have elements these elements, and now you may define an equivalence relation by saying have the same shape. Now they need to be distinguished as elements. I don't know, carpet 1, carpet 2, carpet 3, star 1, star 2, star 3, star 4, circ 1, circ 2, circ 3, circ 4. So they're really different elements, but the index doesn't matter if we consider their shape. I want to make it simple here. The same shape. What are the equivalence classes here? Well, the equivalence classes are, this set is one equivalence class. We could call it, it's the equivalence class represented by circ 1, but obviously it's also the equivalence class of circ 2 and so on. The next equivalence class is this set. And the third equivalence class, and those are all, is this set. And having the same shape is symmetric, it's reflexive, everything has the same shape as itself, it's symmetric, and it's also transitive. And indeed you say, see, this is an equivalence relation. And if we classify and if we build these equivalence classes with respect to an equivalence relation, which you need to have, then you see every element gets covered. And if you now don't look, if you put on your glasses, that are so coarse that they make you see not so clear, but they actually make you see this blurred, so that from far, far away, you only see, it only looks as if the set M contained 3 elements, namely these equivalence classes. Well, that's no longer the set M, because the set M was what was there before. This is then the quotient set. So the set you see here is the set M modulo twiddle. Well, this is obviously just a symbol, but this M modulo twiddle is the set whose elements are the equivalence classes. Okay, so there we have a formal definition. Twiddle be an equivalence relation on M. Then we define the so-called quotient set. It's the quotient set. I already introduced the symbol. It's M modulo twiddle. Looks very dangerous, but it's very simple. And that's the set whose elements are the equivalence classes, M in M. Why can I do this? Well, where do these M's lie? So this looks like universal comprehension, right? So we need to convince ourselves we can actually build this set. So if I write it down like this, it's very likely restricted comprehension, okay? But what is the set that these equivalence classes come from? Well, the equivalence classes are subsets of M. So in which set do all the subsets lie? The power set, exactly. There's an element of the power set of M. Aha, it's restricted comprehension. But then we need to know that the power set of a set is a set. We know this by the power set axiom. Everything is fine. So you see, you in principle always have to check that you can actually construct the object you're constructing. It's hereby restricted comprehension. Anyway, it's exactly this picture. It's the quotient set. Okay. So now remark. Due to the axiom of choice, there exists a complete system of representatives for this equivalence relation, for the equivalence class of these equivalence relations. That is a set R such that there is a one-to-one correspondence, there's a bijection, between the elements of R and the quotient set. Namely, you pick from each class, you pick one element and put it into the set R. And then obviously you represent every single class. How do you pick? Which element do you pick from which equivalence class? Don't know. That's dark. But the guarantee by the axiom of choice is there exists a complete system of such representatives. And that's, of course, very useful. So if you wish, it's gender theory in a nutshell that there are several types of equivalence relations on the same set normally. Okay, a further remark is the following. Care must be taken when defining maps whose domain is a quotient set. And if in this case one uses representatives to define the map. Okay, what do I mean by this mysterious remark? Example. Take as the set M the integer numbers z and define two integer numbers m and n to be equivalent if and only if m minus n is an even number. I hope this is what I want, okay? If m and n is an even number. Now, the first question is this reflexive? Yes, it is, because m is m minus m is 0. 0 is an even number. Good. Is it symmetric, m minus n in 2z? What about n minus m? Well, it's also then in 2z because just the sign changes, and the transitivity is also given. Okay, so this is an equivalence relation. Good. It's an equivalence relation. And if it's an equivalence relation, we can ask ourselves, what is the equivalence class of 0, say, which lies in z? And the equivalence class of 0 is, of course, 2, 4, and so on, but also minus 2, minus 4, and so on. And the equivalence class of 1 is 3 and 5. It's the same as those equivalence classes, minus 1, minus 3, and so on. And so we get the quotient set z mod twiddle consists just of two different elements. I mean, the others are also all in there, but they coincide with this or this one. So as a set, it's the same as this. So it's just the zeros and the ones. Okay, that's this quotient set. And now I could get the idea to inherit addition from z. Idea, on z we have an addition, which we just assume is given at this point. It's the kindergarten addition you do. It takes two integer numbers and it maps them to an integer number. And this guy here, this Cartesian product between two sets, Cartesian product, this is actually the set of all ordered pairs of integer numbers. And what is an ordered pair? Well, that's defined on problem sheet 1. Problem sheet 1, problem 5, subproblem B. Okay, there the Cartesian product is defined. So in A we define the ordered pairs, and in B then the Cartesian product is defined only on the basis of our axioms of set theory, but you of course have an intuitive notion at this point. On Z we have an addition plus, and we wish to inherit an addition which deserves a different name, plus, and this addition is supposed to take two elements of the quotient space and return an element of the quotient space. We wish to inherit such an addition from there, and we could come up with the idea that, or the definition, our tentative definition, and we say, okay, I take an equivalence class, it's an element from here, I take another element from here, and I add them, because that's exactly what this addition is supposed to do. And, well, I have to specify how this works, and I want to define this in terms of this addition on Z. That's what I mean by inherit it. And, well, an idea could be to just take these two representatives one has chosen here. So you see there are brackets around it. But here on the right-hand side, before I put the brackets, I took this representative and I took the other representative, and I used the addition in Z. So the plus without the circle around it is the addition up here. And obviously it can only act on the representatives, because the representatives of this equivalence relation here, they lie in Z. So I pick the representatives, I add them, and after this addition has been completed, only then I take the equivalence class. That's the prescription. But this certainly satisfies our remark, the conditions of our assumptions of our remark, that we actually define a map whose domain is a quotient set. Well, here it's even the Cartesian product of twice the same quotient set, and one uses the representatives, these guys, one uses the representatives to define the map. Now you say, this is my definition and that's it. Well, there is an issue with that, and care needs to be taken precisely because this could be inconsistent, and the technical term in these circumstances is ill-defined instead of being well-defined, could be inconsistent, because imagine the following happens. Imagine you take a different representative for the same class here, but you take a representative A prime, such that it's the same class. And you take a different representative B prime, such that, however, the class of B prime is the same class as B. Then if this addition acts on the quotient set, it should yield the same result, because you use the same classes, you just chose to represent them differently. Now, depending on what you write here on the right-hand side, how you use the representatives, it could be, nevertheless, that if you used a different representative here, a different representative here, that first adding these arbitrarily chosen representatives and then again taking the equivalence class with respect to the predefined equivalence relation could lead to a different result in that case. And it's easy to construct such bad examples. Talk about this later. But I think this one is okay, but you need to check. Check whether choice of representatives matters. So how do we check this? Well, let A prime and B prime such that A prime represents the same class as A does, and B prime represents the same class as B does. Then certainly we hope to be able to prove that with the such defined circ addition on the quotient set, we get the same result, so we write a string of equal signs, that we get the same result as if we added up A and B, the equivalence class of A and B. So let's see what this means. So if A prime is the same represents the same class as A, that means certainly A prime needs to lie in this class because of this property 1 we had before. And then that means that the difference between A and A prime must be in 2Z. And here's the same. So if B prime is supposed to represent the same class, then B minus B prime also lies in 2Z. Now, we can use this and we can say, well, if it lies in 2Z, then there exists an M in Z such that A minus A prime is 2m, and there exists an n in Z such that B minus B prime is 2n for particular B and B prime, for particular A and A prime. Well, it's not an element, sorry, in that case it becomes an equal sign. So we can use this, we can use the definition of circ plus, that would be A prime plus B prime. I just blindly take the two representatives that I happen to have there, and now I replace A prime is A minus 2m, and plus B prime is B minus 2n. Well, that, of course, is the same as A plus B. No? So first associative law, then commutative law. A plus B minus 2 times m plus n. Aha. But A plus B minus 2 times m plus n is certainly the same class as A plus B, because this guy and that guy only differ by an even integer. So by definition they are the same class. But this here I can again, using the definition of circ plus backwards, it's the sum of A circ plus the class of B. And indeed, for arbitrary other representatives, I showed it's well defined. Well defined. So it's only, you only need to take care if for the definition you use representatives. If you manage to write down the definition of an operation on a quotient set without using representatives, no care has to be taken. It's just a normal definition. If you use representatives, you need to do that. Okay? Okay. And so this happens in various shapes and forms and fashions throughout many constructions in mathematics, and in fact throughout many constructions we're going to discuss in this course. So a final section of this chapter is 1.8, construction of integers, and we already talked about them, but I now mean including the operations on there. Construction of integers, natural numbers, integers, rational numbers, and real numbers. So if our axioms of set theory are any good, we're able to construct these important sets. And what I want to give here is an outline. You can certainly write books on various of these topics. What I give here is an outline. Some more details will appear on the next problem sheet, on problem sheet 2. So before I refer to problem sheet 1. So recall that from the axiom of infinity, we got the set n, which by the axiom of infinity was actually called, identified as a set that consists of these sets, 0, 1, 2, and so on. Yeah, 0, 1, 2, 3, and so on are sets, namely which set? Well, the set with name 0 was actually the empty set. The set with name 1 was the set with the element empty set. The set with name 2 was the set with the element and so on, set with set, okay, like this. And by the way, here you see that the computer science 0 is exactly the 0 of mathematics. Okay, so that's wonderful. So that's the set n. But now we wish to establish an addition on n. Wish to establish addition on n. And of course, we should do this in a set theoretic way. We need to derive this from there. And the idea is to define a successor map. And that's a map S that takes an element of n to an element of n. And it's defined by taking the element n of n to the set with the element n. So example, what is the successor of 2? Well, 2 is just a short form of this guy. And so this is the n. And now what I do, I add another layer of brackets around it. And this is just a short form of 3. So the successor of 2 is 3. Wonderful. That's the successor map. Now, in order to make progress, we also need to define the predecessor map. Now, this map is P, and this map is only defined on n star. Star is the, for any set that contains 0, star means without the 0 equals empty set. Okay. Take this one out. So, well, if you want to be set theoretically precise, that is n star is defined as n without this guy and this complement. Did we define it in the lectures? I think we did. Yes. Otherwise, it's on the problem sheet. This symbol here. We did. Okay. It lands again in n. Now, how does this work? To any n we assign, now we need to go backwards. The question is, how do we reduce a layer of brackets? So what do I write on the right-hand side? Well, the trick is to assign to this an element m such that m is an element of n. Now, why does this work? Well, example. The predecessor of 2 is the predecessor of bracket layer, empty set, bracket, equals. So this is n, and now I need to take some element m of n. Well, this set n only has one element, right? And that element is this guy, and this guy is, of course, the 1. The predecessor of 2 is 1. That's the trick to reduce a level of a layer of set brackets. Okay, so we have the successor map, we have the predecessor map, and now we can define the n in nth power, of the successor map, and that is s to the n. What kind of guy is this? Well, it's defined as s after s predecessor map of n. If n, if n indeed comes from n star, because only then can I write this, and we define s up 0 to be the identity. Do I want this? Hang on. Well, it's easier to say here informally if n is greater than 1, and s1 is, of course, simply s. Okay, so that's the predecessor map defined recursively this way. And once we have that, we can define the addition plus that takes two integer numbers and maps them to an integer number by taking this pair mn, which is an element of the Cartesian product. That's precisely what the Cartesian product is. It maps it to this object we want to call m plus n, but its definition is actually given by applying the successor map n times to the m. You start with m and you add n. That means you n times add the successor map. But you see, everything is neatly defined. Example 2 plus 1, what is that? 2 plus 1 is S1 of 2, right? S1 of 2 is S of 2. Did we do this before? Yeah, we did S of 2 before, is 3. Oh, wonderful. And what is 1 plus 2? You say, it must be the same. Well, it looks very different in the beginning. It's S2 of 1. S2 of 1, what is that? That is S after S1, so S of S1 of 1. S1 of 1, well, you believe me, is 2. And this is 3. Oh, it's the same. Okay. That's how this works. Well, this, of course, generalizes. And you get the commutative addition. You can, of course, also show, so general, can also show associative. What about the neutral element? What's the neutral element? Well, it's 0, because m, aha. So not so good here. So we should have started here. I'm sorry. This is live and in color. So you have here S0, and S0 is the identity map on the natural numbers. You do nothing. You 0 times take the successor, you stay where you are, because otherwise we'd have trouble writing down what this is, because m plus 0 with the above definition is, by the definition of the addition, is the 0th power of the successor map with respect to m. So strictly speaking, we have to be more precise here. So this is S1 of 2 is S of S0 of 2, S of S0 of 2, but S0 of 2 is 3. So there's an intermediate step because we have to run the recursion one step further back. Okay, but everything is fine. And now we need to do this. M plus 0 is S0 of m, and then immediately this is m, and 0 plus m, well, you figure it out, it will also turn out to be m. And so 0 is the neutral element of the addition. What about the inverse element of addition? The inverse element would be one where if you pick an element m and you add the inverse element, you get the neutral element. Well, we know that doesn't lie in the natural numbers. 5 plus minus 5 would yield 0, but there is no such thing as a minus 5. So this is not, doesn't have an inverse, so it's not a group. It's not a commutative group. It lacks one of the group axioms, if you want to use that language. And obviously that motivates us to define the integers z. So obviously the increase in your calculational power due to these musings is 0, that's clear. But my point is to show how exactly this follows from the axioms of set theory, and that indeed these axioms all need to be used in order to reconstruct even high school mathematics. And that will be useful later on. integer numbers. I claim that you can define the integers, the set Z, actually as the quotient set of the pairs of natural numbers modulo a suitable equivalence relation twiddle. Now, what is the suitable equivalence relation? So define twiddle on the integer, on the natural numbers as follows. Twiddle on the pairs of natural numbers as follows. You call a pair of natural numbers, Mn, equivalent, well, we'll see whether it's an equivalence relation or not, equivalent to a pair PQ, by definition, if M plus Q equals P plus N. Okay. Now, I just say this, and I'll tell you in a second what the idea behind this funny definition is. But let's first check that this is an equivalence relation. So what about symmetry? If Mn equivalent PQ is then PQ equivalent Mn, where you have to swap M and P, and at the same time you've got to swap N and Q. If you swap M and P and at the same time N and Q, then it's just the sides of this equation are swapped, which is obviously still the same equation. So it's reflexive. Sorry, that was already symmetry. That was symmetry. Reflexive is clear Mn, because this is then, okay, is it right? Yeah, it's then M plus N equals N plus M. This is also clear. And you can also check it's transitive. Let's not do this right now. This is an equivalence relation. Needs to be checked. Okay. Now, what is the intuition behind this? I want to define numbers with a sign, right? That's the basic idea. And, well, you can think of integer numbers as pairs of, so let me write idea, but the idea just goes in a little cloud, so that's not exact mathematics. So the idea is that Mn, this pair, corresponds or stands for M minus N, what we naively would call M minus N. And obviously, if I have two natural numbers, by having a pair of them, I can reach every integer number this way. Okay? That's the idea. And so when are two differences the same? Well, M minus N equals P minus Q if you take the Q to the other side and you take the N to the other side. And then you get this, okay? So that's the intuition. And now you say, yeah, okay, sure, by taking pairs of natural numbers, you reach every integer number this way. But you reach every integer number in many ways. That's clear, because 1 minus 2 is the same as 3 minus 4. Is that right? Yeah, that's right. It's the same integer number. Yeah, that's precisely why we want to identify the same integer numbers. If the two differences are the same, I could have written this as M minus N equals P minus Q. I chose not to do so. Well, I couldn't do so because I don't know what minus means. That's the problem of writing this down directly. But if I take them to the other side of the equation, I have only pluses. So that's the clever idea to actually define this by only using on N that you have an addition on N. That's why you go this way. Then you reach every integer number in various ways, but then you identify these various ways. You put on your equivalence relation glasses that don't see that can't distinguish the different ways anymore, and you get exactly the set Z. Okay. So anyway, it's an equivalence class, and with this equivalence class, we know this quotient set is defined, and I call this quotient set Z. Now, the question is whether this is the Z we normally have. Well, according to these musings, it is, but we might also wish to define or to identify. Normally, we would think like, okay, identify. N, we would think this lies in this set. Well, it doesn't quite lie in this set. It cannot, because this is a set of pairs of integer numbers, well, with some equivalence relation there. So this doesn't make any sense. This can't be true. But what is true is that you can embed n into Z, which is this guy, according to our definition, by saying, well, an n I had in the natural numbers before, I now identify with an element of Z. The elements of Z are equivalence classes. I identify this with the equivalence class of which pair? Well, of the pair n, 0. And in this sense, it lies in there. Okay? In this sense, it lies in there. Yes?
Can you then strongly say that n is a subset of Z or of Z?
No, strictly speaking not, because this has a totally different structure.
Yeah.
But you can make this embedding and say these are actually the elements of n. Right. Redefine the elements of n, and then they are a subset. Okay. That's the idea. You do the same.
Anything more about n being a subset?
No, no. Obviously, because of the definition of the equivalence relation, this is the same as this equivalence class, because they're all identified. That's clear, no? Okay. There's a similar thing with fractions. We're going to maybe look at that in a second. Okay. Otherwise, I'll put it on the problem sheet. So you have this embedding, and then you also maybe wish to define the inverse of a natural number. So let n be in n, and you define minus n. And what is this supposed to mean? Well, minus n would then be defined as the equivalence class 0, n. Do it the other way around. Okay? And this minus n, however, is of course then also an element of Z, obviously. And so you have example 2 plus minus 1. Ah, what is this plus? This must be the plus on Z, right? Have we defined the plus on Z yet? No. We don't know what plus is. We, of course, want to inherit the plus. So definition, we want the plus on Z, well, the subscript Z is Z cross Z goes to Z, but we know that Z is n cross n Cartesian product modulo twiddle and so on. So what we actually have to write down is mn, the equivalence class of this, because that's an element of Z, then plus Z, the equivalence class of PQ. And now we need to define this using only the addition on n that we have. And let's be courageous. This is very likely m plus p n plus q. This is the addition. And what do? We use the representatives to define this operation. So we need to check that this is well defined. Well, the thing it is, intuition is this is m minus n plus p minus q. Well, you add up the positively contributing ones, you add up the negatively contributing ones, and their sum is being subtracted. So that should be the intuition. That's why we define it like this, but the intuition is just the idea behind this definition. That's a valid definition, needs to be checked. It is. It is well defined. And once we have that, we can write down the example. So let's take 2 plus minus 3. Let's take this one. 2 plus minus 3. Well, obviously, this takes place in Z. So you see, every element of Z of this form I denote by its integer number. Right? Every element in Z of this form I denote and so on by this integer number. So what is this? Well, the 2 in Z is 2, 0. It's this rule here. I could have written 3, 1. Okay, 2, 0. Then comes the plus in Z. Then comes the representative or the class represented by one representative of the class minus 3. Well, let's take 0, 3. It's a simple one. Now we take the definition of the plus. This is 2 plus 0, 0 plus 3. This is, of course, 2, 3. Now, 2, 3, however, one can check by the definition of this equivalence relation. 2, 3 is 0, 1. It's the same equivalence class as 0, 1. But 0, 1 has the trivial name minus 1, according to this definition. 2 plus minus 3 is minus 1. Hallelujah. This is how this works. Okay. And obviously, with the integers, we could have defined a multiplication in similar fashion. We could have inherited the multiplication. That's just more of the same. My point here is the basic principle. Questions so far? Everything from axiomatic set theory. Okay. Now, let's do the rationals. Any teachers among you? Teachers? No, no teachers. What a shame. Okay, integers, so rational number. Rational numbers. That works similarly. So first of all, we have to define them as a set. And once we have the set, we can define the operation. And the rational numbers are given by the Cartesian product of Z with Z star. So of the second pair, of the second member in the pair, I take off the 0. Again, modulo some suitable equivalence relation. But now, this equivalence relation on Z, relation twiddle on this Cartesian product Z cross Z star is defined as follows. A pair, let's again call them Mn, but now they're, well, maybe call them differently, xy. A pair xy, sorry, this is too much, sorry. xy, an element of this Cartesian product, is by definition equivalent to a pair uv if v equals u times y. So here we already think of Z as being equipped with both an addition and a multiplication. Okay? So assume we already constructed this. You believe me that this works in similar fashion. And now we call a pair xy of a integer and a non-zero integer equivalent to a pair of such called uv if xv equals uy. And the idea behind this, again, that's the intuition. Intuition idea is that, of course, if in elementary school we write x fraction y, this is just this this fraction thing here morphs into a comma, and the x and the y stand on the left and the right of the comma, and we would like to identify the fraction with this pair. So this is numerator, denominator. But wait, that's not quite true, because the fraction 2 over 3 is the same as the fraction 4 over 6, because well, you can cancel common factors. So it's supposed to be not the pair, but it's supposed to be identified with the equivalence class xy with respect to this. Because obviously, example, the fraction 2/3 is the same as the fraction 2/6, because since 2 times 6 equals 3 times 4. So this implements the rule that by extending the fraction or cancelling factors, you have the same fraction. So this, the glasses you put on now, is you ignore common factors of the numerator and the denominator. Okay? And then it's pretty clear, indeed, fractions are pairs of numbers in the numerator and in the non-zero denominator, but under the identification of cancellations. Very simple, very simple. And in fact, the rational numbers have absolutely nothing to do with division. So in school, one is usually deluded into this idea, well, you know what 8 divided by 2 is, that's 4. Aha, now this is 8 over 2. That's what you're told in schools. 8 over 2 is 4. And then they pretend that this is the same 4 as the 4 in Z. But that's not true, because you have to identify this also as a fraction. Well, it's the same as the fraction 4 over 1, and if you wish, you can embed the integers into the rationals by saying, well, an integer x is now being represented by x comma 1, by x over 1, if you wish. It's the same thing that, so you do not know that 4 over 1 is the integer 4. 4 over 1 is 4 over 1. And then we have this idea, whenever we achieve to get a 1 down here, then we identify it with this integer, and that's this embedding here. It's very much like with the minus signs, before. Okay, and of course you need an addition. You define an addition on Q. That's simple. That's something like xy plus on Q uv. You use representatives, and the addition is what you learn in school. No, it's not what you learn in school. Addition is difficult. Aha. So addition is difficult. You first have to get the fractions to the same denominator. And that trivially can be achieved by writing y times v. Is that correct? Yes. And then you have x times v plus x times v plus y times u. Yeah, that's correct. So this is the rule given for the addition of fractions, and the rule for multiplication of fraction, that's the simple one. That's xy multiplied in Q with uv. That's defined as xu yv, where you should note that this is the plus on z and this is the multiplication on z. So we're always only allowed, of course, to use structure we already have. Now, these are both well defined, as you may wish to check. And here there is the typical ill-defined addition. and that's the fool's addition, yeah, on Q. That's xy plus fool uv, and you define this as x plus u, y plus v. Well, of course, that hurts. Yeah?
Question, how can we talk about real numbers if we haven't defined them yet?
Did I say real numbers? Oh. Just a typo. I'm sorry. Of course, we land there. So if you take the sum of the numerators and the sum of the denominators, you might delude yourself into defining an addition, but here it will actually turn out this is ill-defined. So if you now choose different representatives for the same fractions, this addition will generically yield a different fraction than with the other representatives you chose before. So this is the reason why we insist on using this complicated rule for addition of fractions. It's not because that more corresponds to our intuition about cakes and dividing cakes. It's because this here is simply ill-defined. Okay. So, I mean, there are always attempts to simplify the school curriculum, but this will never come up. It's simply ill-defined. Okay. So because time is up, and there's just one more remark on the reals. Also, the reals can be defined by way of a quotient set. And the set A is the set of almost homomorphisms on Z. And what that is, I assume you will learn on problem sheet 2. And one can actually show that if you define this set and you define a suitable equivalence relation, nice objects like the square root of 2, which of course you cannot find here in Q in the rational numbers, actually lie in this set. So we have the interesting result, final result, that the integer numbers, they can be constructed entirely from axiomatic set theory. Maybe you know this dictum by Kronecker, that the integers were handed to us by God and all the rest is man's work. And well, in our case, the integers are handed to us from axiomatic set theory, and the rest is further work. And so obviously, there are other ways to understand the reals. There are these Dedekind cuts, which are probably more standard. I just present this because this is just one line of always taking quotient sets to define the new set of numbers that you need. And so therefore, we now arrived in, I don't know, high school class, I don't know, what class in high school? 8th, 10th class, high school. With the construction of these real numbers, okay, all from axiomatic set theory. And next time we'll look at topology. That means we go again back to ordinary sets and we select certain subsets of this set M and we christen them open sets, whatever that means, and there will be axioms for what kind of collection of subsets of M you can call open sets. This collection will then be called or any such collection, it's largely not unique, will be called a topology on the set. And topology is the weakest structure you can establish on a set in order, the weakest known structure, in order to define notions of continuity and notions of convergence. See you next time.